Welcome back, Physics 30. So this is the second part of the MP1.4 section. So looking at accelerating frames of references and seeing what happens there, and looking at the principle of equivalence, in that if I'm in an elevator here, of course if it's on Earth, I experience Fg, a gravitational force downwards, right? And if I was out in space, of course, I would experience nothing if I was not near anything. But if all of a sudden, the elevator just shot up like this and accelerated upwards, it would be pressing against my feet, and I would swear that I'm being pulled downwards. And as the principle of equivalence suggests, those are identical scenarios. I have no way of determining whether my elevator is accelerating in this direction and I'm feeling something here, or whether I'm feeling something here because I'm on a planet experiencing a downward force. And of course that brought in an interesting idea here, that if I shone a light from across here and if I was accelerating, it would appear to curve down. Now we don't see curving down here because our force of gravity isn't large enough, but if it were, I would experience the same type of thing, a curvature downwards. So that light is affected by gravity's important prediction of Einstein's general theory of relativity, and it can be tested. The amount a light beam would be deflected from a straight line path must be small, even when passing by a massive object. So yes, we don't see it deflected quite simply because that downward force isn't large enough. And of course, the largest thing we have in our near vicinity is the sun. But if I was looking near the Earth's surface, so the Earth is big enough to deflect slightly, but it's really small, a really small deflection. If I'm, for example, light near the Earth's surface, after traveling 1 kilometer is predicted to only drop this, which is equal to the diameter of a small atom and not detectable. The most massive object nearest is the sun, and it was calculated that light from a distant star would be deflected 1.7 of an arc. Tiny, but you could detect that as it passed the edge of the sun. So if you look over here, of course, it'd be hard to see this unless we were having an eclipse. So Earth, Moon, Sun, if the Moon is here, we could see a star over here, even though the star's location is here. Because if I'm looking at the sun here, I'll just highlight it here so we can see it. Of course, I shouldn't be able to see the star. It's behind the moon and the sun. But as light comes from the sun, it's deflected, kind of attracted, and the sun throws it off, and I end up seeing it, so that the apparent position of the star looks like that, even though it's actually hidden behind the sun. So that's interesting. The mathematician Fermat showed in the 1600s that optical phenomena, including reflection, refraction, and the effect of lenses, can be derived from simple principle that light travels between 2 points using the shortest distance. Thus, if gravity curves the path of light, then gravity must be able to curve space itself. If you can curve light, you curve the space that's around it itself. And that is, space itself can be curved, and it is a gravitational mass that causes that curvature to happen. Indeed, the curvature of space, or rather a four-dimensional space-time itself, is a special aspect of Einstein's general theory of relativity. And of course, that leads right into black holes. According to Einstein's general theory of relativity, sometimes abbreviated the old GR, space-time is curved near massive objects. So we're talking about massive, even more massive than the sun. We might think of space as being like a rubber sheet. If a heavy weight is placed on the sheet, it sags down, as you see here. And this reminds me of one of those donation coin machines that you see, I think in Dairy Queen they usually have them, or some grocery stores like Safeway. So if you had a rubber sheet, threw something heavy on it, it sags down like that. And that weight could correspond to a huge mass that causes space to curve itself. So we have a huge mass here, and it's causing things to curve towards it. Thus, in the context of general relativity, we do not speak of a force of gravity acting on objects. Instead, we say that objects and light rays move as they do because space-time itself is curved around here. So in a way, we don't really talk about Fg or gravitational forces, but we do talk about the fact that the object making the gravity is causing space to warp itself, and anything in that space will want to warp with it. An object starting at rest or moving slowly near a great mass, as seen in figure A, would follow A, the shortest path, leading to that massive object of great mass. So if you look at this great curvature of space itself, could be produced by a black hole, because it'd have to be a fairly massive object to cause that much warping. A black hole has such strong gravity that even light, if it's caught in its path, can't escape from it. To become a black hole, an object must undergo a gravitational collapse, which is the lifetime of a star. Potentially. A star doesn't have to undergo a gravitational collapse, but it could. So it contracts smaller and smaller and smaller and smaller to an extremely small size, but yet you have all that mass compressed in that small space. If an object collapses to within this radius, it is predicted by general theory of relativity that it collapses to a single point, forming an infinitely dense, and the word we use there is singularity, a single point in space which is extremely massive, that has all of that mass just compressed to a single point. This small radius also represents the event horizon of a black hole, and by event horizon we mean the surface beyond which no emitted signal can ever reach us and thus inform us of the events that are happening there. So it'd be like saying, if I had a marble, and if it's caught on top of here, if I let it go, it has no choice but to go down. It's in the event horizon. It's within there. It can't escape. Once it gets going, it can't escape. Slightly above that may not be the event horizon. As a star collapses toward a black hole, the light it emits is pulled harder and harder by gravity, but we can still see it. But once the matter passes within that event horizon, the emitted light cannot escape, but is pulled in by the gravity. And that curvature area is referred to as space-time, curving that in. All I know about a black hole is its mass, its angular momentum, if they're rotating, and its electrical charge. But no other information, no details of the structure of any kind of matter it is formed of can be known, because we can't see information escape it. Now, a couple of years ago, we saw a picture of a black hole, right? But what we actually saw, because how can we see it? We cannot see them because no light can escape them, but we see the interaction of objects around a black hole. So for example, let's say this is a black hole region. Light normally passes by like this, but if we start to see things curve, for example, curving light in an area, or objects that go in this particular area, and yet we don't see anything in that area, well, that could be a black hole, strong enough to curve objects like this, show projectiles going off. Or light itself, we see curving light towards a specific area. That could be an indication of a big black hole. And in fact, that's what you can see. You can't see a black hole itself, but you can see the effects on light rays that pass by or other objects that pass by. All right, so that's the end of MP 1.4. We'll see you again.